37 billion. That is the staggering, mind-boggling number of connected devices that are expected to be operating globally by the year 2025. Now, 2/3 of those are going to be Internet of Things devices, which basically means we are hurtling toward a massive, totally unprecedented global bandwidth crisis. Our current cellular networks, they simply won't be able to handle it. So how on earth do we fix it?
Well, welcome to this explainer. Today, we're breaking down a really fascinating 2023 PhD dissertation by Theresa Melvin Roth. This research explores exactly how the telecommunications industry plans to save our future networks by turning to the absolute wildest frontier of physics, quantum machine learning. We're going to unpack how scientists are trying to harness quantum computing to prevent the internet as we know it from just grinding to a complete halt. Okay, so here's our roadmap for today. We'll quickly cover the 6G bandwidth crisis, the limits of classical computing, the quantum computing solution, the quantum noise problem, fixing those errors with QML, and finally, we'll look at the messy reality of quantum testing.
Let's jump right in. Section 1, the 6G bandwidth crisis.
Right now, we're all using 5G, but looking ahead to around 2030, the telecom industry is gearing up for the launch of 6G. This brings us into an era researchers are literally calling the everything of everything, or EOE. To sustain this, the jump in performance requirements is just massive. We're going from 20 gigabits per second in 5G to an expected 1 terabyte per second in 6G. The latency, that annoying delay, drops from under a millisecond to less than 1/10 of a millisecond. And the device density, it just absolutely explodes. Why? Because 6G isn't just about loading web pages a little faster on your phone. It's designed to support fully immersive holographic media, smart traffic networks, flying vehicles, and massive multi-sensory environments. We're talking about generating roughly 60 zettabytes of mobility traffic every single year. It is a completely different beast.
So, Section 2, the limits of classical computing. You might be wondering, why can't we just build bigger cellular towers and faster traditional computer chips to handle all this? Well, for decades, we've relied on Moore's law, the idea that we can just keep shrinking down transistors and packing more of them onto a single microchip. But it turns out that strategy hits a literal physical brick wall at about 10 nanometers. When you get down to that microscopic level, classical Newtonian physics completely breaks down. Electrons no longer orbit predictably like planets around a sun. Their orbits blur, and they actually start acting according to the strange rules of quantum mechanics. So to power 6G, the telecom industry can't just scale up what we already have. They have to completely cross over into the quantum realm.
Which brings us to Section 3, the quantum computing solution.
To hit the speeds and the scale necessary for a synthetically intelligent 6G network that can manage itself in real time, the industry absolutely must pivot to quantum computing. And the core difference between classical and quantum computing lies right here. Classical computers use regular bits, which are totally deterministic. They're either a 0 or a 1. Absolute certainty, right? But quantum computers use quantum bits or qubits. And thanks to quantum mechanics, a qubit can be a 0, a 1, or, and this is the crazy part, both a 0 and a 1 at the exact same time.
That specific, mind-bending ability is called superposition. It essentially means an object exists in a combination of multiple simultaneous states. Think about it like this. If a classical computer has to calculate the absolute best route for thousands of flying 6G delivery drones, it has to calculate every single route, one by one. But a quantum computer, using qubits in superposition, can calculate all those potential routes simultaneously. It solves incredibly complex logistics instantly, logistics that would completely paralyze our current classical networks.
Sounds great, right? But wait. Section 4, the quantum noise problem. A quantum network sounds perfect, except for one massive complication in this scientific quest. Quantum computers are incredibly, ridiculously fragile. When a qubit loses its quantum state, it's called decoherence. And honestly, almost anything can cause it. A slight temperature fluctuation, remember these machines have to be kept near absolute zero, a tiny vibration or straight environmental noise. But the absolute craziest cause? It's something called the wave-particle duality measurement problem. Basically, simply observing or measuring an unknown quantum state actually causes the wave to collapse into a particle. The mere act of looking at the data destroys the data. Talk about a headache.
Because of this extreme fragility, the qubit communication error rate, or QCER, is exorbitantly high. We're talking about nearly 100% data loss in some extreme cases. Right now, our current single-core quantum processing units, or QPUs, are so noisy and error-prone that they rarely even finish practical, non-trivial programs without just crashing completely.
Let's look at how this actually impacts the physical architecture of the hardware. Current full-stack quantum computing relies on a single core design, where they hardwire qubits directly to the processor, which makes them super susceptible to these errors. But to actually handle a massive 6G network, we have to evolve to a multi-core setup. Catch? To connect multiple quantum cores, you need a highly stable internal quantum network layer that can teleport quantum information without dropping it. And right now, all that quantum noise is completely preventing that from happening.
So how do we get around this? Section 5. Fixing errors with QML.
How are scientists trying to fix an impossible noise problem where you can't even look at the data? Well, that was the core focus of Dr. Roth's research. The proposed solution is a highly experimental process called quantum error detection and correction. Remember, we literally can't look at the qubits to see if there's an error, because observing them destroys them. So the process works in 3 theoretical steps. First, we encode physical qubits into a network of logical ones. Second, we train a quantum machine learning algorithm to sense the wave patterns and detect the error, whether that's a bit flip, a phase flip, or a combination of both. Third, the system actually autocorrects the state without ever directly measuring the delicate quantum data itself.
To try and pull this off, the study tested a highly advanced algorithm. Okay, get ready for a mouthful. It's called an unsupervised entangled quantum generative adversarial network, or a uQGAN. The name is complicated, but the concept is brilliant. A generative adversarial network essentially pits 2 neural networks against each other in a game of cat and mouse. You have a generator creating fake quantum data and a discriminator trying to tell the fake data from the real data. By entangling both the real and fake data together at the discriminator, the network theoretically teaches itself to automatically recognize and suppress errors completely on its own.
All right, let's bring it back down to earth. Section 6, the reality of quantum testing. Everything we just talked about, that's the high-level theoretical physics. But what actually happens when you plug this into a multi-million-dollar quantum computer and run the experiment? Well, in the middle of this intense, groundbreaking research, there was a massive plot twist. An unexpected outage on Google's quantum computer forced the researcher to switch the entire study over to IBM's quantum computer right in the middle of the experiment. Now, quantum computers aren't like switching from a Mac to a PC. They use entirely different base logic gates at a hardware level. Google defaults to CZ gates, while IBM uses C0 gates. Because of this real-world tech glitch and the sudden vendor switch, the entire trajectory of the experiment fundamentally changed.
And here are the results the study ultimately reported. The uQGAN model actually failed to learn. It did not show an association with reducing the error rate. Why? Well, it turns out that on the IBM system, a specific sampling parameter that was required for the algorithm was actually missing from their public release. The model literally couldn't properly execute the experiment. But rather than being a failure of the scientific theory, this beautifully highlights just how immature, unpredictable, and incredibly difficult working with current noisy intermediate-scale quantum hardware truly is. We are still in the very, very early Wild West days of this technology.
But you know, beyond all the gates, the qubits, and the failed algorithms, I think it's absolutely vital to remember the human element here. Real people are pouring their lives into building this futuristic foundation for us. I actually want to read a quote directly from the heartfelt acknowledgments of this dissertation. Directed at the researcher's husband, she wrote, "My depth of gratitude for your patience and support cannot be articulated using man-made linguistics, much less measured using any instrumentation created by Newtonian physics." I just love that. It really grounds the science, reminding us of the immense dedication behind every single attempt to push our technological boundaries forward.
And that brings us to the ultimate question we're left with today. As the Internet of Things just completely explodes, and the 6G everything of everything era barrels toward us in the 2030s, this bandwidth crisis is very, very real. So, will we crack the code of quantum machine learning? Will we master quantum noise and build fault-tolerant multi-core quantum networks before our classical cellular bandwidth simply runs out? It is literally a race against physics, and it's a field you are absolutely going to want to keep your eye on. Thanks so much for joining me on this explainer, and hey, keep questioning the science.